So here we're going to work through our group work in section 12.1, looking at 3D coordinates. All right, so for the first few, we're trying to just get a feel for what some different solution sets look like. And so for the first one, we have x equals z and z equals 2. We have two different equations, so these are going to intersect and give us something. And maybe we'll just go about this kind of with way one, where we just take each equation in turn and see what things look like when these intersect. All right, so we're going to be in 3 space, and so I'll just toss out a big 3 space to start. All right, x equals z, we can think about that kind of by analogy. You know, if we had a line x equals y, right, that would just be the solution set, you know, this diagonal line, right, at 45 degrees. That was what we'd get if we had x equals y. Where x equals z, we're going to have something similar. But here, this is going to be in the xz plane here. And again, we're going to be coming out at kind of 45 degrees. But notice, since y is not involved at all, this diagonal line that we've just drawn inside the yz plane is going to spread out right and left, right in that y direction. And so kind of doing that, we'll get this kind of plane. It's kind of awkward to get the perspective here. But if you can imagine the plane, if we tilted this up, it'd be straight along the YZ plane. And now we're just kind of taking that, let me kind of draw it like this. Here's the YZ plane. If we take that, this plane and kind of push it forward, here we are with our plane x equals z. All right, next we got z equals 2. So here, z equals 0 would just give us the xy plane. Z equals 2 is going to push that up 2 units, equals 2. And so we're going to have a plane that cuts through that point on the z-axis. So all the points in 3 space with z coordinate 2. We get a plane that looks like that, and these two planes are going to intersect. Let me maybe choose a different color. These are going to intersect in a line. The picture is not quite perfect, but there it is. If that was a perfect line, it should be. Okay, it's getting worse. I'm going to stop. There we go. There's the line of intersection that we get. That is going to be the solution set for this system of equations, this line. One other way to think about this is, well, if x equals z and z equals 2, well then x and z both equal 2, and y can be whatever it wants. And so, you know, this point here, if we want, it's going to have x coordinate 2 and z coordinate 2, and y can be whatever it wants, stretching in that forward and backwards direction infinitely. We get our line. All right, moving on. X squared plus y squared equals 4. The first thing I notice when I look at this is that there's no y, not y, but there's no z going on, right? There's no z involved at all, so we can just imagine that this is a 2-dimensional picture and then bring this into 3 space if we'd like, right? So in 2D, this would give us a circle of radius 2 in the xy plane. Right, and so if we try and now bring that into 3 space, this picture that we drew, we can kind of sketch that here in the xy plane. Here we've got a little bit of perspective, so our circle is going to look a little bit wonky. something like that. There we are. All right, so there is just one section of our shape. But here, since z is not involved in our equation, we can take this section here and we want to stretch it in the positive and negative z directions, right, forever. And so if we do that, we take this, this circle and slide it up and down, we're gonna get traced out this like infinite tube, right? This cylinder goes like this, right? And it would just keep on going up forever, but that's hard to draw. So we just cut it off at a certain point. And this one here is going to be coming down forever as well. Again, that same circle at each section. All right, so that's what we get from that equation. Our next equation is x plus 1/2 y plus z equals 1. And so here we're given the hint that since the equation's linear, its solution will be a plane. Well, then this, of course, begs the question, well, how do we get a picture of a plane? And hopefully you played around with this a little bit. Maybe it felt awkward, and that's good. That's part of the learning process. Let me give us a helpful way to think about this. What if we weren't talking about planes? What if we were talking about lines? How many points would we need before we could draw a reasonable sketch of a line? We'd need 2, right? If we had 2 points, if we had a line that goes through those 2 points, well, we could connect the dots, and that's going to be part of the line, and the rest of the line, right? We just extend it infinitely in the direction that that segment gives us. So for lines, we need 2 points. For planes, three points, I claim, is what we're going to need. If we have 4, that'll work, but I claim that all we need is 3. And a nice set of 3 points to get a hold of are our axis intercepts. So where our plane cuts through the x-axis, y-axis, and z-axis. Hopefully it does somewhere. And we can find out pretty quickly where that is. So for example, if we want to find out where this thing hits the x-axis, well, wherever point it hits the x-axis on, we know 2 of the coordinates. But if it's on the x-axis, well, then its y-coordinate has to be 0, and its z-coordinate has to be 0. All right, so we actually now know those 2 points of information. We can use that to figure out what x we need. So on the x-axis, both y and z equals 0. And so if we take our equation up here and plug that in, then we're going to get what, x plus 0 equals 1. So x equals 1 is our point, and let's give it some scale. I'll say that this is that point right there at x equals 1. So our plane cuts through this point. All right, what about the others? Well, on the y-axis, we'll have x and z equal to 0. And so subbing that in for our equation of the plane, we'll get 0 plus 1/2 y plus 0 equals 1. So multiplying by 2, we'll get y equals 2. And so if that's 1, this point over here is that y equals 2. And our plane cuts through at that point. All right, last but not least, z-axis, this is going to be where x and y are both 0. And so subbing into our equation, we'll get 0 plus z equals 1. And so right at 1, yeah, that's not there. Okay, right at 1, that's another point that our plane cuts through. And so notice we got these 3 points, and what we can do at this point is just connect the dots. So if we just draw a straight line connecting the pairs of points here, what we get then is a nice triangular chunk of our plane, and we can kind of see it has some slant to it. And the way that we can think of this defining the whole plane is much the same as, this line segment over here defines the whole line. And if we just extend according to, the slant that we get from this segment. Well, here we have this slanted triangle. Well, if we now just go ahead and extend out on all these sides, right, according to the slant that this triangle gives us forever, then we will indeed define the plane that our equation up here gives us, right? If we just imagine if we were stepping on this triangle and just walked off straight and kept on walking in any direction, right, that's going to be the plane that we're describing here. All right, now let's talk about distance. Let's find the shortest distance from this point to some different things. All right, so first off, let's get a feel for where this point lives. All right, so where are we at? So 4 in the x direction, something like this. -2 in the negative y direction. All right, here's the negative y-axis. And, all right, so there's -2. It's also right here. And then, up 6 in the z, so something like that. There we are. So there's 6, and also sliding over here, that's the 6. It gives us our point here. Beauty. All right. So what's the shortest distance from this point to the xy plane? Well, the xy plane here is just down here, and the fastest way to get there is straight down, right? And so actually it's this z coordinate of 6 that is the shortest distance to the xy plane. So that distance up here is 6. Well, what about to the xz plane? Okay, so here, maybe let me trace that in here. All right, that's this plane. It's supposed to be this plane, right? That goes through the x and z axes, positive and negative, right? Extends forever, right? Well, if we want to get this point, push it towards this plane in the shortest distance possible, we just want to go straight there, which is following the y direction. Right? And so actually, this is a terrible picture because of how I've drawn this. Let me try this. Let me try this one more time. Right? Oh, oops. Okay. Bear with me. All right. So here we go. Let me kind of cheat. There we go. So it's this distance of, that we moved over -2 to get to our point, and so this distance here that's going to land us on the xz plane is that 2. All right, so that's going to be the distance from our point to the xz plane. All right, let me get these out of the way. What about to the y-axis? So here now, we're not going to a plane where we're trying to push this point, the shortest distance possible to the y-axis, which is hanging out back here. And again, the fastest way to do that, the shortest distance, is just going to be straight there. And if you can imagine kind of moving our eye to behind this point, we're just going to push it. And we're going to push it so that actually, we're not changing this y distance at all. So we're going to still keep this -2 the whole way. And we're just going to go straight there. This line is going to be the fastest way to push this point onto the y-axis. And so it's this distance that we're going to be trying to find. And actually, if you looked at this from the side, what we'd have here is a right triangle. Right, the side view here, we can imagine that, would look like this. Here we have the positive x-axis, positive z-axis, and we have our point hanging out, and we're just trying to push it straight. Okay, going back is not serving me well. Straight onto the y-axis, which is kind of looking, I guess, the other way. This is kind of the side view from back here. There's an eyeball. And so we get this nice right triangle. And so we can just use good old Pythagoras to help us out. Right, the distance down here at the bottom, that's going to be the 4 that we came out. We have the 6 up top. And so, well, if we have 4 on the bottom and 6 up top there, this distance here from Pythagoras, we call that d. What are we going to have? We're going to have 4 squared plus 6 squared equals d squared. So d is what? Square root of 16 plus 36, which is 52. So it's root 52. So that looks like that's the distance there. Yes, I agree with myself. Okay, moving on. Oh wait, no, we have one more, don't we? So the y-axis distance is root 52. Now the distance to the point 1, 2, 3. So that's over at 1, 2, 3-ish. So now we're looking at this distance here. And with this one, something's different than this last situation here. We're actually moving from this point to this point. We're going to be changing our x-coordinate, our y-coordinate, and our z-coordinate. We need a 3D formula for distance, and it's a beautiful generalization of the 2D formula that we're used to. We just have differences of all of our components squared, and then square root of the sum there. All right, so if we want to find the distance to the point 1, 2, 3, cranking into our formula here, I'll just make use of this. So our second point, I'll make that 1, 2, 3. So what do we have? We got x2 is 1, then the x from our first point is 4. So 1 minus 4 squared, plus the y from our second point, which is 2, minus the y from our first point, which is negative 2 squared, plus the z from our second, which is 3, minus the z from our first, which is 6. And so what do we get here? Sorry, I'm getting crowded here. So negative 3 squared is 9, plus 2 plus 2 squared, which is 16, and then negative 3 squared, which is 9. And so do we get 18 plus 16? So 34, root 34. I believe so. All right. All right, next, we're in flatland, right? So yeah, from our nice distance formula, we get a nice sphere formula just by choosing a center point and a distance, a radius. And so here we're imagining that we are a sphere, and we're intersecting here with flatland. And so here, if we're supposing that flatland has equation z equals 1, we want to know the intersection we get with our equation here. Well, the way that we intersect things is by taking one equation and substituting it into the other. And so here, the cleanest way to do that for sure is to take the z equals 1 and sub that into our second equation just by replacing that z with what it equals, 1. And so doing that here, this is part A, finding the intersection of our sphere, with flatland. We'll get what, x minus 2 squared plus y plus 1 squared plus, substituting in, we have 1 minus 3 squared, which equals 9. And so what over here, this is negative 2 squared, and so that's 4. And so if we subtract that over, the equation that we're left with, a nice standard form here, it's going to have 5 on the right-hand side. All right, so there's our equation. The second part asks, what's the radius of our intersection with flatland? Well, here, the way we get that is just by taking the square root of the number over here, right? So the radius is root 5, right? And so this would be the equation and the radius of our intersection here that we're making with flatland. All right, part B here asks, well, what if instead of z equals 1, what if the equation was z equals 0? What would a square see? And actually, well, once we know that, our sphere has radius 3, and it's centered at the z at 3, well, if it's moving down 3 to flatland, we're only going to see the very bottom tip of our sphere intersecting with flatland, and so we should only see a point. And there's other ways to kind of make that deduction, but that's one way to think about it. We should just see a point, single point in flatland. How can we see that algebraically? Well, again, we're intersecting our sphere with flatland, and so if flatland's equation is z equals 0, then that's what we would plug in, substitute in for z here. Right? That's going to be a clean way to go about it. And so just to see what we'd get, x minus 2 squared plus y plus 1 squared plus 0, substituting in, minus 3 squared equals 9. But now we get negative 3 squared, which is 9, and so subtracting that over actually gives us the equation x minus 2 squared plus y minus 1 squared equals 0. And so kind of geometrically, the way we could think about this is that it's a sphere with radius 0, which is a point. Algebraically, what we have going on is that we have something squared plus something squared equals 0. Well, the only way that can happen is if both these things we're adding up actually equal 0 themselves. And because otherwise, if it was anything positive or negative, when you square it, we get stuff that's positive and we wouldn't get 0 anymore. So this tells us that x minus 2 equals 0 and y plus 1 equals 0, i.e. x equals 2, y equals negative 1, and that is just a single point. All right. If you haven't read through this excerpt from Flatland, it's a lot of fun. I encourage you to read through that. But that's it for now. I'll see you next time.